This is a control room in a typical power plant. At the moment, these operators are busy performing the specific tasks required for starting up one of their boilers. The procedures that they're following may be different from the ones you'll be required to follow when starting up your boilers. However, what you have in common with these operators and the operators in other power plants are procedures. Regardless of the size, type, or output of a boiler, each plant has specific procedures that operators must follow to start up and later shut down a particular boiler. While these procedures differ from plant to plant and from boiler to boiler, they are followed for two important reasons: to protect the boiler from damage and to protect you and other plant personnel from injury. Throughout the remainder of this topic on boilers, we'll be looking at various plant procedures. In this program, we'll cover some of the basic start-up and shutdown procedures for both a drum-type boiler and a once-through type boiler. Now, procedures, like the boilers used in power plants, differ considerably from unit to unit. Procedures are written for a specific boiler and a specific plant. One thing that is common to all procedures, however, is the fact that operators are required to follow them to the letter. For any operator, plant procedures should be considered as the final word on how equipment is operated. They can only be changed by authorized supervisory personnel. Before you attempt to operate any piece of equipment in your plant, make certain that you know and understand your plant's procedures on how that equipment is to be operated. Before we begin looking at some of the basic procedures for startup and shutdown, there are a number of things that you need to keep in mind. First of all, the startup and shutdown of a boiler are complicated jobs requiring a great deal of training and experience to accomplish properly. The purpose of this program is to give you a general overview of what is usually involved in the startup and shutdown of a boiler. Your instructor can help you apply this information to the specific procedures used by your plant. Secondly, during startup and shutdown, operators may be required to monitor various instruments and components in the plant. The examples we'll use are, again, typical of what you can expect to find in your plant. For specific information, consult your plant's operating procedures. The final thing that you need to keep in mind while viewing this program is that the procedures we discuss are generally performed by more than one operator. For the most part, there is at least one operator working in the control room during startup and shutdown, and at least one operator stationed near the boiler. In this program, no attempt is made to separate the duties of a control room operator from other operators working about the plant. The reason for this is simple. Every operator working on startup or shutdown of a boiler must be familiar with all of the procedures that apply to these operations. In this way, you can be assured that equipment will be operated properly and startups and shutdowns will take place smoothly and safely. Okay, with these things in mind, let's move on and cover some general considerations about startups and shutdowns. One overall concern of an operator during startup and shutdown is the protection of the boiler and personnel in the plant. By protecting the boiler, you protect plant personnel. Now, regardless of the type of boiler that your plant uses, it is designed to produce steam at a designated pressure and temperature. The pressure and temperature of the steam is relatively high. Pressure can be several thousand pounds per square inch, and temperature can be several hundred degrees Fahrenheit. These high pressures and temperatures present the potential for causing you problems unless they're carefully controlled. One such problem is that of expansion. When a boiler is first started up, the temperature of its metal components increases. Here, for example, is an igniter control box on the side of a cool boiler. Here is the same box after the boiler has been operating several hours. Notice the difference in the height of the box in relation to the floor. The increase in temperature causes the boiler to literally stretch. It is not unusual for the overall length of a boiler to increase as much as 12 inches during startup. Unless this expansion occurs evenly, the boiler casing, water wall tubes, headers, and other components may be damaged or even rupture. This can create a safety problem in the plant and affect the useful life of the boiler. By the same token, during shutdown, the metal components contract as their temperatures decrease. Contraction must also occur evenly to prevent damaging components. The expansion and contraction of boiler components is caused by the pressures and temperatures under which the boiler operates. Firing rate is the control that an operator has over temperature and pressure. Firing rate is a general term that refers to the amount of fuel burned and steam generated. In today's modern plant, the firing rate is normally controlled either manually or automatically from remote controls like these. One way of thinking about firing rate is to consider it as the method that an operator has for adding energy to a boiler. The energy we're talking about, of course, is heat. Now, once you put the energy into a boiler, you have to get it out if you want to use it to do work. Useful energy leaves a boiler in the steam, and wasted energy leaves the boiler in the flue gases up the stack. As you know, in order to maintain a constant supply of steam, you need to provide a boiler with a constant supply of water. So if firing rate is the method for controlling the energy going into a boiler, the turbine control valves are the means of controlling the energy leaving the boiler. And drum level control is designed to prevent any mismatch between feed water flow and steam flow. Firing rate and water level are two important controls that the operator has over a boiler. By properly controlling the firing rate and maintaining the proper water level at all times, you are protecting the boiler from damage. In a little while, we'll begin looking at some of the procedures for starting up a drum-type boiler. For now, though, read over the material we've just covered in your text and answer the questions. If you need additional help with any of your material, ask your instructor to assist you. Earlier, you learned that two of the principal ways that an operator has for protecting a boiler are water level and firing rate. Obviously, you have to establish a water level in the boiler and fire in the furnace before you can control them, and that's part of the basic procedures for startup. We'll begin by following an operator in this plant through the basic procedures for a cold startup of a controlled circulation drum-type boiler. A cold startup means that this particular boiler has been out of service for an extended period of time, and its metal is at room temperature. Your plant may have separate procedures that are used for starting up boilers that have been offline for shorter periods of time and whose metal temperatures are higher. Later on, we'll follow an operator through the shutdown procedures for this boiler and then move to another location and look at startup and shutdown of a once-through boiler. In preparation for startup, the first thing you need to do is become thoroughly familiar with the startup procedures in your plant and the location and function of all the components associated with the boiler. Plant prints and procedure manuals, if your plant has them, are valuable tools for gaining this information. Now, assuming you've done your homework and know your equipment and procedures, the first step in startup is to walk the system. This operator is doing just that. He's walking the system to make sure that everything is ready for startup. One of the first checks he makes is of all openings into the boiler. Manholes, observation doors, and other openings should be closed during startup so that pressure can be established and maintained. Making sure that observation doors are closed can also be a necessary safety consideration. During startup, it's possible for a balanced draft boiler's furnace to go positive, causing flame to blow out of any opening on the furnace. Another check that an operator makes during a walkthrough is the position of all valves. This is often called valve lineup or lining up the system. It simply means that all valves associated with boiler operation are either open or closed according to the plant's procedures. The proper positioning of valves is critical to safe boiler operation. During startup, an adequate flow of water, fuel, steam, and air is necessary to establish combustion and to protect components from the effects of heat and pressure. An improperly positioned valve could prevent fuel or air from getting to the burners or cause a pipe to rupture under pressure. By walking the system and making sure all valves are properly positioned according to your procedures, you ensure that the boiler and plant personnel are protected. Also, during a walkthrough, the operator should check the bearings on all moving equipment needed for startup. Here, the operator is touching each bearing on the motor of the air preheater to check for excessive vibration and temperature. The operator also checks the lubricant level on the bearings to make sure sufficient lubrication is available in accordance with his plant's operating procedures. During the operation of any boiler, the operator receives important information from indicating instruments. While doing your walkthrough, you need to check that gauges, sight glasses, and other instruments that you'll need are in service and available. Other checks that are normally made during a walkthrough include verifying that there is sufficient condensate available for the production of steam and that coal bunkers, oil tanks, and similar storage facilities have been filled according to procedure. You also need to make certain that all fuel supply lines and oil burners are isolated from the boiler furnace prior to startup. This keeps the furnace free from combustibles, which could cause an explosion if accidentally ignited. Once the walkthrough is complete, the next step in the startup procedure of a drum-type boiler is the filling of the steam drum and water-side components. The steam drum holds a large quantity of water for the production of steam. The drum also directs boiler water to the headers and water wall tubes. In preparation for startup, the operator opens the valves that control the flow of feed water to the economizer inlet and boiler water to the drum. Filling the drum accomplishes two things. First, it forces most of the air from the water wall tubes, and second, it brings the drum to an acceptable firing level. Now, the firing level and normal operating level in a steam drum may be different on your boiler. As you know, a typical steam drum is between 1/3 to 1/2 full of water during normal operation. On this steam drum, the normal operating level is 1/3 full. However, the operator knows to fill it 6 to 8 inches higher than the normal operating level prior to startup. This higher level is required to allow for the decrease in level which occurs when the boiler water circulating pumps are started up. By contrast, on natural circulation drum-type boilers, it's not uncommon for the firing level in the drum to be lower than the normal operating level. A lower level is necessary in this case to allow for the expansion which takes place when the water in the water wall tubes begins to boil. From earlier training, you should know that as the temperature of water is increased, bubbles begin to form that increase the volume of a given quantity of water. For example, in this laboratory setup, the water level in this flask, where boiling is taking place, is higher than in this flask where no boiling is taking place. The increase in level is called swell. On natural circulation boilers, the increase due to swell may cause the level in the steam drum to exceed acceptable level specifications. This could cause water to overflow into the superheaters. By filling the drum to a level that is lower than normal operating level, you allow for the increase due to swell. Once the steam drum is filled to an acceptable firing level, the next step is to begin taking the appropriate action to establish a continuous flow through the boiler. The continuous flow of water, which later becomes steam, is important for a number of reasons. Two of the most important are to ensure a continuous supply of steam for the production of electricity and to cool the boiler and its components. Without proper flow, increasing temperature and pressure could result in overheating and boiler damage. On this boiler, water wall circulation is initiated by starting the boiler water circulating pumps. When the appropriate pumps are started, the operator monitors the drum level and anticipates the decrease in level. He then makes any adjustments necessary to maintain the proper level in the drum. At this point, what we've done is establish the continuous circulation of boiler water to the drum, downcomers, lower headers, water wall tubes, outlet headers, and back to the drum. There is presently no steam in the boiler since we haven't started any burners. However, in preparation for lighting off the boiler furnace, we must provide the means for a continuous flow of steam in order to protect the boiler and its components from overheating. The economizer in this boiler receives feed water from the hot well of the condenser. With no steam being produced, the source of condensate is limited to the condensate storage tank. In order to protect the economizer from overheating during the initial phases of startup, the operator opens a recirculation line valve that allows water from the lower headers to recirculate through the economizer. The recirculation line ensures that the economizer will not overheat or boil dry when the furnace is lit off. Your plant procedures may have another method of protecting the economizer. If so, your instructor can explain how it's done. On this unit, the economizer recirculation line remains open throughout the remainder of the startup procedures. With the economizer protected, the operator next opens appropriate vents and drains in the economizer, steam drum, superheaters, and reheaters. Here, he's opening vents on the steam drum according to this plant's operating procedures. There are a number of reasons for opening vents and drains. On the headers, for example, drains provide a flow path for condensate. On the steam drum, vents provide a means of removing air from the boiler. And on the superheaters, vents and drains provide a flow path for steam during startup and shutdown. With the drains and vents opened, we've completed the steps to prepare the boiler for lighting off, and we've made sure the boiler is protected from damage. By protecting the boiler, we protect the people working around the boiler. As you recall, we walked the boiler to make sure that everything that we needed for startup was available and working properly. Next, we filled the steam drum to the appropriate firing level and started the boiler water circulating pumps to ensure a continuous flow of water through the system. Finally, we prepare the boiler for a continuous flow of steam by opening appropriate vents and drains. In a little while, we'll continue following the startup procedures through the necessary steps for lighting off the furnace. For now, read over the material that we just covered in your text and answer the questions. Your instructor can help you apply this information to your specific plant. So far, in starting up the drum-type boiler, the operator has made sure the system was ready for startup by walking through the system that he'll be operating. He's also filled the steam drum and associated components to an adequate firing level to provide a continuous flow path for water. And he's opened appropriate vents and drains to provide a continuous flow path for steam. In this part of the program, we'll continue following the basic procedures for startup through additional preparations. Then, we'll light off and warm up the boiler. The first task in preparation for light off is to start the air preheater. As you know, the air preheater raises the temperature of air entering the boiler by using flue gas as a heat source during normal operation. Once the air preheater is started, the next step is to establish a continuous flow path for air and gas through the boiler. This boiler is a balanced draft boiler that uses both forced draft fans and induced draft fans to circulate air and gas. With this system, the operator first starts the induced draft fans. The induced draft fans draw air out of the boiler and establish a slight negative pressure throughout the furnace area. Once the induced draft fans are in operation, the next step is to start the forced draft fans to increase the amount of airflow through the boiler. On boilers that operate under a positive pressure, it is only necessary to start the forced draft fans, since these systems do not have induced draft fans. The flow of air to the boiler is controlled by the positioning of dampers on the forced draft fans. Your plant's procedures will indicate the appropriate damper positions to provide the proper flow rate. Airflow to the boiler is monitored on these indicators in the control room. The fans are allowed to run for a designated period of time to purge the boiler of any combustibles that may be present. The amount of time necessary to purge the boiler is typically between 5 and 15 minutes. Purging is a safety consideration prior to starting the igniters. If the boiler is not free of all combustible material, an explosion will occur when the igniters are started. Once the boiler is purged and the operator is satisfied that conditions are right for proper air and gas flow, he's ready to begin adding heat to the boiler. This coal-fired boiler has burners like these located in each corner of the furnace. Coal and air enter the furnace through these burner ports. The coal is ignited by oil igniters located here. There is also a removable warm-up burner that uses oil located here. On this boiler, oil is used for both ignition and warm-up. This is because at low firing rates it provides a more stable and reliable flame than pulverized coal. The igniters and warm-up burners may also be used during normal operation to help support combustion. This is particularly useful when the coal is wet or of poor quality. The igniter burners are started by a spark from a large spark plug, similar to what you find in an automobile engine. The operator usually sparks the igniters from the control room. Once ignited, the igniter burners are used to light off the warm-up oil burners and later the coal burners. Let's look at how the igniters are lit off. With the igniter sparking, the operator starts the igniter fuel oil pump and opens the air atomization lines so that when ignition oil flow begins, proper mixing between the oil and air will occur. Starting the fuel oil pump also opens the oil supply lines to provide the necessary fuel for ignition. The oil is atomized by the air and ignited by the spark from the igniters. At this point, the operator may have to make fine adjustments of the fuel and airflow so that the igniter flame becomes stable and reliable. These adjustments are normally made in the control room by changing the set points on controls such as these. During the course of adjusting the igniter flame, the operator may make a visual inspection of the furnace area by opening observation doors on the boiler to satisfy himself that ignition is taking place properly. When all the igniters required by his plant procedures have been lighted, the operator proceeds to the next phase of operation, lighting off the warm-up burners in the boiler. Warm-up burners can take on a variety of designs and use a number of fuels. The function of warm-up burners is to provide a means of gradually increasing the temperature and pressure of the boiler water to a point that the main coal burners can be ignited safely. If the boiler is not properly warmed up, the intense heat produced by lighting off the coal burners could cause uneven expansion of boiler tubes and other components, which would damage the boiler and require that it be shut down. This boiler uses removable oil burners for warm-up. When the igniter flames are stable, the operator inserts a warm-up burner into the burner port. He pushes the burner through the port several times to clear away any ash or slag that may have accumulated in its opening. He then connects the burner to the port and opens the valve on the line supplying atomizing air to the burner. Next, he opens the valve on the oil supply line. The operator then makes a visual inspection of the boiler to be sure that proper ignition has occurred and that the warm-up burner is burning properly. We have now introduced heat into the boiler. Several hours will be required to raise the temperature and pressure in the boiler and to bring the water in the water wall tubes to the operating temperature. As I told you earlier, firing rate is one of your principal means of controlling the production of steam and the temperatures and pressures in the boiler. It is important that you keep the firing rate within the specifications of the boiler manufacturer. Most procedures will indicate the ramp rate for boiler warm-up. Ramp rate means the change in temperature of the boiler per unit time. In the case of this boiler, temperature is increased no more than 150 degrees Fahrenheit every hour. This gradual increase is necessary to protect the boiler components from thermal stress. During the warm-up period, it is also necessary to carefully monitor the water level in the steam drum. As the temperature of the water in the water walls increases, steam bubbles begin to form. Remember that in preparing the water side of the boiler, drains and vents were opened to provide a flow path for this steam. As the steam passes through these vents and drains, it removes water from the steam-water circuit. Careful monitoring of the water level in the drum is important to ensure that none of the components boil dry. After an appropriate period of time has elapsed, so that the boiler is sufficiently warmed up according to procedures, steam is being produced. The next step in the startup procedures is to roll the turbine. Your plant will have specific procedures which deal with turbine operation, which we won't cover in this program on boilers. Turbines are mentioned here because they are the reason that most power plants have boilers. When the turbine has been rolled, the operator monitors the steam flow to the turbine and makes sure that it is sufficient and reliable according to his procedures. In this plant, when steam pressure reaches 50 psi, the operator can begin closing down the vents and drains on the superheaters, reheaters, and steam drum. The vents and drains are normally left slightly open until a load is established on the turbine. This ensures a constant steam flow through the superheaters. Let's review quickly what we've accomplished so far in starting up this boiler. We began with the understanding that a continuous flow of energy through the boiler is important to power plant operation and the production of electricity. We first provided a flow path for water and steam through the boiler. Then, By turning on the induced draft and forced draft fans, we provided a means for a continuous flow of air and gas through the boiler. The airflow also purged the boiler of any combustibles to make conditions safe for introducing a fire in the boiler. We then started the igniters and established a flame on the warm-up torches to gradually increase the temperature and pressure in the boiler and begin the production of steam. When steam pressure and temperature reached an appropriate value indicated in our procedures, we rolled the turbine and closed down the vents and drains. Throughout these procedures, we've carefully monitored the firing rate and drum level to make sure that the boiler is protected and the components do not boil dry. The final aspect of boiler startup is establishing and stabilizing an appropriate flame in the boiler furnace. This flame allows the operator to efficiently produce the steam required for the generation of electricity. We'll look at that part of the startup procedure in a few minutes. For now, read over the material we've covered in your text and answer the questions. Your instructor can clear up any material that you're having trouble with. Now that flow paths have been established for water, steam, air, and gas, and we've warmed up the boiler, the final step in the startup procedures is to establish a proper boiler flame. The fuel used to fire this boiler is coal. Therefore, the operator must know and understand the proper procedures and equipment for coal handling. His first concern is to provide a means for coal to reach the burners. To do this, many of the steps in the procedures must be repeated several times to get the boiler up to normal firing level. Coal is transported to the burners by primary air that is directed through the pulverizers. As with warming up the boiler, establishing fuel flow must be accomplished gradually to allow all of the fuel to burn completely. Therefore, the operator begins by starting one of the many pulverizers that will supply coal to the boiler. With the pulverizer operating, the operator next adjusts air dampers to direct secondary air into the boiler. This is to ensure sufficient air for complete combustion when fuel is supplied. He next starts the appropriate coal feeder to supply the fuel for combustion. With the feeder on, he adjusts the flow rate according to his operating procedures. With fuel going to the pulverizer, the operator now adjusts the primary airflow to the pulverizer to first dry the pulverized coal and then transport the coal to the burners. The dried pulverized coal is carried to the coal burners by primary air. At the burners, the coal mixes with secondary air, forming a combustible mixture that is ignited by the igniters. The operator continues to adjust the supply of fuel to the burners by slowly increasing the flow rate through the feeders. When the appropriate fuel flow for the pulverizer is reached, the operator can repeat these steps with a second pulverizer if load demands call for it. The steps are repeated for all of the pulverizers that supply the boiler as demand requirements increase. As each pulverizer is brought up to speed, the operator checks the boiler flame to make sure that combustion is occurring properly and that all of the burners have ignited. He then makes any necessary adjustments in air and gas flow through the boiler by increasing or decreasing the damper openings on the forced draft fans and induced draft fans. Depending on the load demand and the specific procedures for plant operation, the igniter flames may be extinguished once the coal burners have ignited and the boiler flame has stabilized. You need to check your plant's procedures about this phase of the operation, since abnormal circumstances may require that the igniters be left on. With a flame established in the furnace, the operator continues to monitor all systems so that he maintains the boiler within the prescribed specifications of his plant's procedures. At this point, startup procedures are complete and normal operating procedures are followed to ensure safe and efficient boiler operation. What we have shown you so far are basic procedures that are typical of what you'll be doing when starting up a boiler in your plant. Once again, these are typical procedures, and your plant may not follow them exactly the way we've shown you. Your instructor can help you apply this information where it differs from your actual procedures. What most startup procedures boil down to are a series of steps that establish a controlled flow of water, steam, fuel, air, and gas through various systems of a boiler. In the next part of the program, we'll go over the basic procedures for shutting down a drum-type boiler. For now, read over the material we've covered in your text and answer the questions. Ask your instructor to help you if you're having any problems. In this part of the program, we're going to look at some basic procedures for shutting down a drum-type boiler. Once again, I'd like for you to keep in mind that specific procedures differ from plant to plant. What you'll see here are typical of the basic procedures that you'll have to follow when working in your plant. You also need to keep in mind that there are a number of reasons for shutting down a boiler. Because of this, the procedures that you'll need to follow will vary depending on the circumstances requiring the shutdown and how long the boiler will be offline. Basically, shutting down a boiler is the reverse of starting one up. You reduce load, reduce feed water flow, cut off the fuel supply, and purge the furnace. All the while, you monitor firing rate and water level in the drum to protect the boiler and plant personnel. The first step in shutting down the boiler is to reduce the firing rate according to proper procedures. Reducing the firing rate affects the temperature and pressure on the boiler. As with startup, temperature and pressure must be reduced gradually to protect the boiler. This is known as ramping down, and in this plant, the operators reduce the firing rate no faster than 150 degrees Fahrenheit per hour. Check your procedures for rate acceptable for your boilers. As load decreases, the operator begins to reduce the fuel flow to the burners. This is done by taking pulverizers offline one at a time. When taking a pulverizer offline, the first step is to reduce the airflow to the pulverizer. At the same time, you reduce the fuel flow from the feeder. Your plant's procedures will indicate how the flow rate from the feeder is to be reduced and when it is appropriate to shut the feeder off. When the feeder is shut down, the operators continue to run the pulverizer until no coal is left inside. This reduces the chances of pulverizer fires caused by spontaneous combustion. With these pulverizers, when the pulverizer temperature reaches 100 degrees Fahrenheit, the operator can be sure that there are no combustibles left inside. At that point, the pulverizer can be shut down. As firing rate continues to be reduced, the other pulverizers will be shut down one at a time. The forced draft and induced draft fans are left running to purge the boiler of all combustibles. With all the pulverizers offline, no heat is being added to the boiler. However, the temperature inside the furnace is still very hot, and some steam is still being produced. The next step in shutdown procedures requires that the feed water flow to the boiler be reduced. This is done gradually to make sure that a sufficient level is maintained in the steam drum while the boiler furnace begins to cool down. As the furnace cools, so do the tubes in the superheaters, reheaters, and other steam-carrying components. To prevent an accumulation of water in these areas, the operator opens drains to provide a flow path for the water. It is important to prevent water accumulation in steam-carrying components to minimize water hammer and the carryover of water droplets into the turbine. With the boiler vents and drains open, the next duty of the operator is to begin shutting down the boiler water circulating pumps. In general, one pump is left on to help cool the boiler. When the boiler temperature reaches a designated value, the remaining pump is shut down. Up to this point, we've stopped fuel flow, steam flow, and water flow to the boiler. The only thing left is air and gas flow. The forced draft and induced draft fans are left running to continue purging the boiler of any combustibles and as an aid to cooling down the boiler. Wind box dampers, observation doors, and manholes can also be opened to help cool the boiler. The methods for cooling down your boiler will depend on the reason for the shutdown. As I said earlier, there are a number of reasons for shutting down a boiler. If the boiler is going to be down for a day or two because of a reduction in demand for electricity, then the operators will not cool down the boiler completely. On the other hand, if the boiler is going out of service for maintenance, then it will be necessary to cool the boiler down to a temperature that is safe for maintenance personnel to enter the boiler and make repairs. In some cases, the boiler may be offline for an extended period of time, say several months. In these cases, it may be necessary to cool the boiler completely and then fill it with non-corrosive gas or water to protect its components. Your instructor can explain the various procedures used by your plant for shutting down a boiler and protecting it while it remains idle. The procedures for starting up and shutting down a once-through boiler are slightly different from the ones we've looked at so far. In a little while, we'll take a look at how this is done. For now, read over the material on shutdown in your text and answer the questions. So far, we've concentrated on the basic procedures used for the startup and shutdown of a typical drum-type boiler. In this part of the program, we'll shift our attention to the procedures used on a typical once-through boiler. From your earlier training, you know that during normal operations, most once-through boilers operate at pressures and temperatures at or above the critical point. That is, at temperatures and pressures where there is no distinguishable difference between water and steam. This means there is no need for a steam drum to separate steam and water. There is also no need to recirculate water through the steam-water circuit of a once-through boiler. However, during startup and shutdown, once-through boilers require a long period of time to reach critical conditions, and the separation of steam and water becomes an important consideration. Now, there are a number of similarities between the startup and shutdown procedures for drum-type boilers and those used for once-through boilers. In this part of the program, we'll quickly review the similarities and then concentrate on the differences. In preparation for startup, an operator of a once-through boiler performs similar duties as the operator of a drum-type boiler. That is, the operator walks through the entire system, making sure that bearings are properly lubricated, that valves are lined up, and that everything required for a startup is available and in service. During the later stages of the startup procedures, the operator ignites burners and brings pulverizers online in a similar manner as with conventional drum-type boilers. The primary difference between startup and shutdown of a once-through boiler and a drum-type boiler is the requirement of a separate system for the separation of steam and water during the startup and shutdown mode of operation. We'll use this block diagram of the flow path of water and steam through a once-through boiler to explain the different modes. During the normal operation of a once-through boiler, Any given quantity of water is transformed into steam in one pass through the steam-water circuit. The water is first supplied to the economizer, then the water wall tubes. In the water wall tubes, the water is subjected to pressures and temperatures above the critical point, causing it to transform into steam. The steam continues from the water wall tubes through the primary and secondary superheaters, the high-pressure section of the turbine, back to the reheat section of the boiler, and on through the intermediate and low-pressure sections of the turbine. During startup and shutdown, however, the pressures and temperatures under which once-through boilers operate are below the critical point. This means that there is a steam-water mixture in the water wall tubes. For this reason, a separate system is required that uses a flash tank to separate the steam-water mixture. A basic system includes a flash tank, 2 isolation valves, and a control valve. We'll look at the startup mode of operation first. In preparation for startup, the control valve between the water wall tubes and the primary superheater is closed, and the isolation valves on either side of the flash tank are opened. Water is directed from the economizer and water wall tubes to the flash tank. Excess water is drained from the flash tank to the condenser. As the operator increases the firing rate, a steam-water mixture forms in the water wall tubes. This mixture is directed to the flash tank. Inside the flash tank are moisture separators and dryers similar to those found in conventional steam drums. These components make it possible to separate the water from the steam. The steam continues from the flash tank to the primary superheaters, secondary superheaters, and on through the HP turbine, reheater, and IP and LP turbine sections. Water remains behind in the flash tank and is drained to the condenser. Throughout this phase of the startup mode of operation, the procedures for startup are very similar to those of a conventional drum-type boiler. However, after a period of 6 to 8 hours, the temperature and pressure of the once-through boiler reaches the critical point. As this occurs, the isolation valves on the flash tank begin to close, and the control valve begins to open, changing the boiler over from the startup mode to the normal once-through mode of operation. The changeover usually occurs automatically, and in this plant, it's primarily controlled by a computer. However, manual changeover is possible as well. Even though this plant uses a computer to assist the operator must still monitor the process to make sure that the changeover occurs according to proper procedures. During the shutdown mode of operation, the conditions are reversed. The boiler is operating at temperatures and pressures above the critical point. As the operator reduces the firing rate, the temperatures and pressures on the boiler drop below the critical point. When this happens, the isolation valves on the flash tank begin to open as the control valve begins to close. The resulting steam-water mixture is directed to the flash tank where steam and water are separated. When the turbine is tripped, the isolation valve supplying steam to the primary superheater trips shut. The flash tank is then vented to atmosphere to keep pressure in the flash tank from increasing. Water in the flash tank continues to drain to the condenser. The need for this separate system for the separation of water and steam is the principal difference between the startup and shutdown of a once-through boiler versus a drum-type boiler. Again, keep in mind that what we've shown you is usually typical of a once-through boiler. Your procedures may be different. Your instructor can help you adapt this material to your particular plant. Well, in this topic, we covered the basic procedures that are required for starting up and shutting down drum-type and once-through type boilers. In general, these procedures follow a few basic steps. First, you fill the components of the boiler with water. Next, you provide appropriate flow paths for water, steam, fuel, and air. And finally, you control the firing rate and water level in the boiler according to proper procedures. By following the designated procedures used in your plant, you can be sure that the components of the boiler will expand or contract uniformly, and that the boiler and plant personnel are protected. We'll take some time to finish reading this section of the text and answer the questions. Your instructor can help you if you're having any problems.